Good morning and greetings, everyone. So this is the slide of title of my presentation, Generating Privacy Preserving Synthetic Medical Data. And I'm Fahim Faisal. So I'm going to present the paper. So this is the overview. And moving on to the problem statement and motivation. So here we can see four X-ray images. In the first X-ray image, in the top left corner, there are the name of the first and last name of the person, the birth date and age of that person. So in the top right corner, there are some personal information and including some diagnosis information. So such scans contain patients' sensitive information. So hospital use patients SSN or SIN to identify patients in this system, and any kind of linking or re-identification attack may breach those private information. So one thing we can do is that anonymize those header or text data, or like selectively remove or codify identifiers in the metadata. So for an example, in the MRI image, we can do one thing, that we can strip the skull, but in that case, we can see the segmentation accuracy reduced, so the utility reduced. And if we remove the header information in the X-ray image, the same person can be re-identified with like 95% accuracy. And it is tough to standardize such things, because like in some countries, in the X-ray image, the header is in the top left corner. In some countries, the written information is in the top right corner. And sometimes defacing in face recognition algorithm, it also reduces utility. But in medical domain, re-identification and reduced utility is a big risk. So we know that deep learning and computer vision can help us to increase the reliability of the conventional findings. But deep learning based medical models are data hungry. They require a lot of data, and federal law do not allow us to use private information of the patient. So one solution is that using reliable synthetic data that can maintain utility. And one challenge is to generate high stake domain data generation with differential privacy guarantees. So to face that challenge, we came up with this paper. So here were able to generate reliable private X-ray images with differential privacy, which may encourage data collection and make it more available and understandable for patients. It can preserve higher utility or reliability in high-stake domain. So the main reason for reliability is that selective noise mechanism, and we introduced a noise-free discriminator, which helps to generate reliable data. And we use the W-GAN's loss, where it preserves the one Lipschitz property of W-GAN to battle mode collapse and vanishing gradient problem. So those are the two major problems in GAN data generation, which also ensures implicit noise clipping. So here we used relaxed notion of differential privacy, which is a rainy differential privacy, which reduced the privacy cost due to better composition. And we were able to train the model for longer time, and we were able to train deep more architecture. So and one thing that sometimes patient like hospital need, that they will store the data locally, and they don't want to provide the data to a central server. So in that setting, they can they can provide that they can train the model locally in a federated setting. No need for manually selecting beans like in the previous approaches. So those are the generated images, just a glimpse of them. So why do you need differential privacy? So like anonymization doesn't work due to re-identification and link in attack. So the main problem of machine learning algorithm is that they memorize private data. So what's our expectation? We expect that a model should make similar prediction irrespective of the presence of the training data. So to enforce an upper bound in privacy leak and to quantify privacy, the concept of differential privacy came, where if the D and D prime are two data distribution with where a difference of one single sample or single data point. So the we try to reduce the privacy breach less, and the upper bound is epsilon, and adding sigma, we can epsilon delta privacy can can relax the notion a little bit. So one of the existing approaches is the DPSGD. So using DPSGD, the authors sample a mini batch of the training data, and they calculate the par example gradient, and they clip the gradient, and they added some they averaged the clipped gradient and added some Laplacian noise to that. The problem of such approaches is that it with epoch, it increases the privacy loss increases geometrically, because for example, for n epochs, the privacy budget becomes like n times epsilon. So For the solution, some authors proposed a rainy differential privacy. So we incorporated that rainy differential privacy in our algorithm. So it's a relaxed differential privacy. Instead of using the log ratio of probabilities, it consider like distance between two distribution, which is the rainy divergence. So here D and D prime are the two distribution, and it has like here the we are able to use Gaussian noise, which has a composable property to ensure smooth peak, and most of the data lies within the two standard deviation. So due to the additive property, when like after multiple mechanism are applied on our on data, so for example, for each epoch, if the privacy budget is epsilon 1, epsilon 2, so the budget adds up, and they don't get multiplied. So then the so it provides strong guarantee under composition and natural generation of the differential privacy, and it provides tighter upper bound and no parameter growth under iteration, because in deep learning we require a huge number of iterations. So it also satisfies differential privacy when lambda is equal to infinity. So in the GAN training, we can see that we are providing the noise to the generator. So the generator is generating like fake images X set, and it's providing all the real and fake images to the discriminator. So the generator is trying to fool the discriminator, and at the same time, the discriminator, who's the critic, will give back score and feedback to the generator. So it will try to distinguish between real and fake images. So for real, it will provide a value of 1, and for fake images ensure that the value of 0. But such kind of like 1 and 0 ceiling creates some problem like vanishing gradient and mode collapse. So instead of like using BC loss, we use the W loss of Wasserstein gang again. So it uses distance between real and fake distribution, and the generator tries to minimize the distance between real and fake distribution, which helps to reduce the mode collapse, and which eliminates the ceiling of 0 and 1. So in that case, the discriminator can provide more meaningful feedback. So we try to train the generator and the discriminator at the same level, ensuring like none of the model is overfitting. So in the sanitization process, which is a very important process here, so as we are using the WGAN's loss, so the one Lipschitz property ensures that the norm of the gradient is one within every data point within the training procedure, and it increases stability of the training. So in differential privacy, we have to set clipping hyperparameter C. On the basis of this C parameter, we clip the gradient before updating to limit the information during each sample's impact. So in that case, like the implicit noise clipping of and as WGAN, it helps to eliminate the search for such expensive hyperparameter C value searching, and a different C value are very sensitive, so they depend on the like learning rate and other hyperparameters of the model, so they may create clipping bias. So it also helps to eliminate clipping bias. So in this case, it can be eliminated using gradient penalty or like noise gradient clipping, but in that case, like we are using gradient penalty. So in the this is a extra term which is added to the loss with which is multiplied with lambda, which is a hyperparameter. So to compute the gradient penalty, we are actually subtracting 1 from the norm of the gradient of the interpolated image. So this ensures a stable training. And from the previous slide, we have come to know that a stable discriminator and the meaning and the better discriminator necessary, because in medical field data should be reliable. So our discriminator can tell us how much realistic the data is, and on the basis of such data, the medical doctors will or practitioners will perform many like come up with different results depending on the like diagnosis task. So to increase the accuracy of the generated data, we decided to keep the discriminator noise free, which helps to provide meaningful feedback, and it can preserve more gradient information. But as the generator is in the central server and can exploit the data, so we are trying to ensure the a private generator, so that each example may not have significant impact on the model's encoded weight. So to do that, we are like clipping the gradient of the generator, but no, we are in that case we are not clipping the whole gradient, we're clipping a partial part of the gradient that is directly impacted by the real data. So in this case, we have to keep the generator in the central server, and we have to we can release the generator, not the discriminator. But if hospital wants to train their own discriminator, and if they want to release the discriminator, so they can train the data locally in a federated setting where the discriminator can also be released. So in the GAN sanitization workflow, So we are providing noise to the generator, and the generator is generating X-ray image and passing the synthetic image to the discriminator. The discriminator is generating loss based on the real and fake image. So as it has already seen the real image, so the back propagated loss has like private information, or gradient has private information. So we like sanitize the propagated gradient of the discriminator that is coming to the generator, but not part of the generator that is not exposed to the real data, that is only exposed to the noise. So we are like sanitizing partial part of the generator's gradient. So, and the fourth case is the distributed learning. So here there will be a private generator in the central server, and the private generator will, like, the differential privacy of the generator will help it to keep it safe from reconstruction risk. And there are multiple discriminators that will be trained in different hospital, and different hospital helps to improve diversity in the generated data. And we ensure that the light discriminator is lightweight, which can be easily trained in any edge device in the hospital. So we followed a like policy from previous approaches, that is we pre-train the discriminators, so that the discriminator becomes more efficient. So in this case, we only communicate the sanitized gradient to the server. So in that case, any if someone assumes that the server is not honest, then in that case, the server cannot exploit the weight, because the weight is already noisy. So, and it is an unlabeled generation, so there's no need for label. So hospitals may it will encourage hospitals to provide more data, and it ensures more efficient communication, as the discriminators that are locally trained, they only like transfer a smaller number of trainable parameters, because the discriminator is lightweight, and only the gradient that are exposed to the real data are transferred. So in case of membership inference, we also ensured that the like our diagnosis model is free from membership inference attack. To ensure that, we used high regularization. We used like dropout of high rate within two layers. As previous work showed, that regularization helps to reduce generation gap, and it also prevents memorization and overfitting, as we are training the data on the real synthetic data, but testing it on the real data. So it will prevent overfitting. And though we are using synthetic data, so but we also try to ensure dual protection against membership inference attack, so that client's training data cannot be re-identified. So in the experiment, we consider two settings. In one setting, we have used the MNIST dataset, because most of the previous differential privacy-based generators used MNIST and FMNIST, because they are low resolution. To compare the benchmark, we use the MNIST, and for our privacy, for medical privacy, we use the Kaggle chest X-ray images, where we generated 24,000 synthetic data, and it took 3 days to train with the 3060 GPU, and number of iterations were 2,000. A noise scale larger than zero point 0.1, which is zero point 0.7, is used here. So in previous approaches, a noise scale less than like larger than zero point 0.1 generated a very blurry or like noisy image, which was not clear. But in our case, it came up with a very good image, which is clear. So in MNIST, we can see it gave a better result than like previous state of the art methods. And in X-ray images, we can see that it generated better result than DPSGD, and it the result is almost comparable to the result when the real data is used. So to analyze the impact of privacy budget, so the privacy cost is epsilon, which is 3.19 into 10 to the power 4, and the delta is 1 into 10 inverse minus 5. So like we compared quality of image varying noise multiplier. So we in the left side there is a normal patient data, and in the right side there's pneumonia patient data. So noise multiplier controls the how much noise we add to the image. So in left and right side, in the first column, we are using a noise multiplier of low noise multiplier, which is 0.02, and the image quality is really good. But in the right side, we are using a noise multiplier of 1.02. In that cases, in the previous approaches, the image became really noisy. But in our case, we can see that still the images quality is not that bad. So in the for the more qualitative comparison, we modified the DivGAN architecture to come up with some generated images, X-ray images. So the DivGAN usually used like one channel image, and it was like applicable for low resolution images, so we had to modify the architecture. So after modifying, we came up with the result. The top image shows the result of the DivGAN, and the lower image shows the result of the our approach. So in the DivGAN, we can see that there is a mode collapse occurring, because there's less diversity and one single X-ray image is being repeated. But in our case, using the WGAN's loss, it helped to battle the mode collapse, and we can see diversity in the generated X-ray images. And we used a high noise multiplier of 0.7, but still it generated a better result. So those are the real images that are used for training, and those are the generated images. So for qualitative analysis, we are showing the normal patient's data and the pneumonia patient's data, which is generated using a noise multiplier of 0.7. So in privacy and communication, so in the federated setting, we were able to reduce reconstruction risk and membership inference risk because we are using a highly regularized model and private model, and we are able to reduce the privacy cost using relaxed differential privacy, which is 7.99 into 10 square, which was up to 9.99 into 10 to the power 6 before in Fed AVG GAN. So we are able to reduce the privacy cost, but we are also able to reduce the communication because communication cost, as we are using a lightweight discriminator, the number of parameters that is being transferred during the federated setting is very low, and we are able to ensure and only the we are able to ensure that the gradients that are transferred to the central server, they are exposed to the real data, so the partial gradients are being transferred. So the communication cost was reduced by a lot. So moving on to the conclusion. So we are able to generate high quality radiology data with differential privacy guarantee in both distributed and central setting. And the most important thing for medical data, we are able to ensure reliability via stable and noise-free discriminator. So hospital can train the images locally if needed, and there's no need for experts because the data can be unlabeled. And we hope that it will work as a stepping stone to create awareness to protect medical data privacy and motivate researchers to conduct more research in this privacy domain. So we showed that it is possible to generate high-stake medical domains data with differential privacy despite high noise. So in future work direction, we want to come up with better generative architectures like transformers or stable diffusion based models. But we also want to use domain adaptation, which can improve the performance on noisy and real data. So in that case, maybe we will be able to generate some better quality result, and we want to extend it for other types of medical image data. So that's all from our group. So those are the references. Only 5 top references are mentioned here. The rest of all the references are mentioned in the paper. And thanks. If you have any question, you're welcome to ask. Thanks a lot.